Hello, this is going to be my last lecture in this course on structural dynamics, and what I will be ending off with is looking at a couple of example problems, one dealing with flexural deformations and one dealing with axial deformations. Although I started my course of continuous systems by looking at axial deformations, I will look at the example of the axial deformations a little bit later. I'll start off with the flexural deformation problem, primarily because I want to highlight some very specific thing about the axial deformation problem. Okay, so let's start off. So this particular lecture, this final lecture of this course, is going to be on examples for dynamic response of continuous systems. Okay, and in this let's start off with looking at a example for flexural deformations, and in this particular case there is no need for me to look at the equation that I developed in the last lecture, which was the beam, the Timoshenko beam, where you consider flexure, shear, as well as rotatory inertia, and of course always linear inertia. So I will solve a very simple problem, and that is that of a simple beam constant m bar EI, no rotatory inertia, no shear distortion, okay, only flexural deformation and point mass for the cross section. Okay, and this is subjected to a where, so this is a uniform load, okay, where P bar of t is looks like this. So it's a suddenly applied load. So this is a suddenly applied load on this particular one, and of course, you know, initial conditions are 0. So you have 0 and v dot x bar is equal to 0. Okay. So first and foremost, we have to write down the equations of motion. And what are the boundary conditions? This, since it's a simple beam, the boundary conditions is phi 0 is equal to 0, phi double prime is equal to 0. Why? Because moment is 0 here. Similarly, phi L is equal to 0, phi double prime L is equal to 0. So we've written down the equations of motion, and P bar x of t is nothing but P bar of t. So it is not a function of x. Okay. Now, so this is the first step. So this is step 1. We've done step 1. What's step 2? I'm going to do this in a very algorithmic way. Step 2, free vibration. Now, I am not going to go through this. In this particular case, this is a simply supported beam, simple beam. We know what the solution, we've already evaluated the solution. It is sine n pi x over L, and omega n is equal to n squared pi squared E I upon m bar L fourth, and for n going from 1 to infinity. So, we have done the free vibration. I have already done it before. So, there is no need. Step 3. What was step 3? Step 3 was generalized mass and loading. How do I find that out? Well, let me find out. M n is equal to 0 to L phi n squared x m bar x dx. In this particular case, it is m bar into 0 to L sine squared n pi x upon L dx. Now, note that how do I solve this sine squared? Well, you recollect that cosine of 2 n pi x upon L. Okay, if you have sine squared theta, let us say, okay, cosine 2 theta is equal to 1 minus 1 minus 2 sine squared theta, and utilizing that you can plug that in and you will get this equal to, for all n, it is equal to m bar L by 2. So, m n is equal to m bar L by 2 for all n. Okay? Note that you understand that here this is solved by the fact that cosine 2 theta is equal to 1 minus 2 sine squared theta. So, this one you just make it into this. So, it becomes that sine squared theta is equal to cosine 2 theta plus minus 1 upon 2. So, this is what you use to solve this. I am not going to solve that. Okay. The next one is P n. So, I am still on step 3, finding out the generalized mass and the generalized loading. P n is equal to phi n x p bar x over t dx. So, this is equal to p bar sine n pi x dx, and this, if you look at it, is equal to p bar L upon n pi, there is minus 0 to L cosine n pi x upon L. So, this basically becomes equal to minus p bar n pi cosine n pi minus 1, and if you look at this cosine n pi is equal to plus 1 when n is even, and cosine n pi is equal to minus 1 when n is odd. So, therefore, what we get is p bar n is equal to 2 bar p L upon n pi for n odd and 0 for n equal to even. Okay? This makes sense, because if you have, see, this is a UDL. If you look at your first one, this one into this gives you a product. If you look at the second one, it is like this, halfway. So, if this is positive, this is negative, and the area under that curve is 0. But anyway, we have solved all of that. So, it is an even. Okay? And so, this is p bar n. And so, therefore, now what we have is we need to step 4 is to solve m bar y n plus omega n squared m n y n is equal to P n. So, therefore, now obviously with what y n 0 equal to 0, y n dot 0 equal to 0, because if you plug in, remember we could get y n in terms of this v x of t by taking integral 0 to n phi n x v x of t dx upon m n. Okay. So, we can do that, and if that v x of t is equal to 0, automatically y n and y dot n are going to be equal to 0. So, if you put that in for n equal to even, y n of t is equal to 0. Okay. For n equal to odd, y n of t is equal to, well, let us see what it is. You have P n is 2 p bar 0 L upon n pi, that is your this is the load part. So, that is P n, and that upon omega n squared m n. So, omega n squared, and m n is what? M n is equal to m bar L by 2. Sorry. Yeah. Okay. Into 1 minus cosine omega n t. Okay. So, let us see what this turns out to be equal to. Let us have a look at what this term turns out to be equal to. The L cancel. Okay. So, what we are left with is 4 p bar 0 upon n pi omega n squared m bar. Okay. Now, let us see what omega n squared is equal to. Omega n squared is equal to n squared pi squared, right, into sorry is n fourth pi squared into E I upon m bar m. So, if I plug this in, what do I get? I get that y n of t is equal to 4 p naught. Now, look at this, omega n squared is n fourth pi fourth. So, what you have is n to the power of 5, 5 to the power of pi to the power of 5. Okay. So, n to the power of 5 E I. Okay. So, what you have over here is, yeah. So, this is what you get, and P 4 upon E I into I am sorry, this is P I m bar L fourth. Okay. So, there is an L fourth term that comes over here, which goes on the top. So, it becomes L fourth over here. So, y n turns out to be this. So, if I were to look at y n, okay, if I were to look at y n, what does my y n, y 1 look like? Let us look at y 1. See, I am going to rewrite this, y n of t is equal to 4 L fourth upon n to the power of 5, 5 to the e to the power of 5, 1 upon this, into 1 minus cosine omega n t. So, if I look at y 1 of t, what does y n of t look at? If I look at y n of t, what I get is 4 P0 L4th upon pi 5th upon 1 minus cosine omega 1 t. Y 2 is of course 0, y 3 of t, it is only the odd ones that stay. So, it is 4 p 0 L 4th. Now, n is 3 to the power of 5, that is 81. So, it is 243 pi 5th upon 1 minus cosine omega t, and so on and so forth. Well, let us look at y 5th. You get 4 p naught bar L upon, now look, 5 to the power of 5 is 625 into 5, which is 3125 pi to the power of 5 E I 1 minus cosine 3 cosine 5 L. So, now if you look at this, so these are my y1, y3, y5. Okay. So, now if I look at my v of t, my Vx of t is equal to summation n going from 1 to infinity phi n x into y n of t. So, if you look at it, this is equal to, if I were to just plot this, this would be 4 p naught L 4th by p 5 E I. I am going to put it outside. Okay. Now, you will see, if you look at this, this becomes actually like 5 by 384. It is very close to 5 by 384. Okay. Into the first one is 1 minus cosine omega t into sine pi x by L. Okay. Then plus, now think about it, this is 1 minus. So, there is a 243, 1 upon 243 into 1 minus cosine omega 3 into sine 3 pi x upon L plus 1 upon 3125 1 minus cosine omega 5 sine plus so on and so forth. Note something very, very interesting. You look at these terms. For all practical purposes, this term, even these terms are almost negligible. And if you look at this, the first mode, okay, if you were to look at it, if you look at static Vx, what is it going to be? 5 by 384 p naught bar L 4th by 5 pi E I. Okay. This is what you get. Okay. So, if you look at this, if you look at this particular term and you look at this, you will see that these two are almost identical. There is very little difference between 5 upon 384 and 4 upon pi to the power of 5. Okay. In other words, what we are saying is, you will see that 4 pi is almost equal to 5 by 384. Okay. And this, if you look at it, is like pi squared. I'll just explain to you. Okay. Pi squared would be about 10. This would be about 100 and 3.84 into 100. Okay. This basically becomes like 314. Okay. So, 4 upon 314 is approximately 5 upon 384. Okay. So, it becomes it's very close to each other, and for all practical purposes, we can see that the first mode dominates the response. Remember, even in multi-storied things, I had pointed out that displacement is essentially governed by first mode. In this particular case, you see very clearly that the first mode, if you look at the coefficients, these coefficients are so small that for all practical purposes, even though this is supposed to be in an infinite series, if you take just the first term, okay, you'll almost get it equal to the value. Okay. So that in a sense is displacement response. Now let us look at, we've got the displacement response. So now let's look at the force response. Let me look at bending moment. Okay. So I'll look at, so this was step 5, now step 6. Okay. Evaluate mx of t. Let's look at mx of t. What is mx of t? Bending moment at any instant is equal to EI del squared V by del x squared. Okay. So what do we have? If you look at it, what is Vx of t equal to? Vx of t was equal to 4p L4th upon EI into 1 minus cosine omega t into sine pi x upon L plus 1 upon 243 1 minus cosine omega 3t sine 3 pi x upon L plus 1 upon 3125 into cosine omega 5 into sine 5 pi x upon L. Okay. So differentiate this. If I differentiate this, what do I get? What is del squared V by del x squared? Del squared V by del x squared is equal to the following: 4 p naught L4th upon pi 5 EI 1 minus cosine omega. This one doesn't differentiate, but this one differentiates, and this one differentiates to what? It differentiates to minus n squared pi squared. So this is like pi squared upon L squared into sine pi x upon L plus 1 upon 243, and this, when you differentiate sine 3 pi, what do you get? You get minus 9 pi squared upon 243 into 1 minus cosine omega 3 into sine 3 pi x upon L plus, now if I differentiate, it becomes 25, of course minus again, upon 3125 1 minus cosine omega 5 into sine 5 pi x upon L plus plus plus. But let us look at this very interestingly, and that is that what does this term turn out to be? Okay. So, if I write down the moment, okay, I get m x of t equals 4 p naught L4th upon pi 3 EI, and there is a L squared in every term. So, that L squared becomes p naught L squared okay, P naught L squared, okay, and inside we get 1 minus cosine omega bar t into, I have taken, by the way, this is minus because the minus, all minus go out. So, this becomes sine pi x by L, then plus, now if you look at this 9 upon 243, okay, 81 and 27, right? Yeah, 27. So, this becomes 1 upon 27, 1 minus cosine omega 3 sine 3 pi x upon L. And now, if you look at this, if you look at 25 becomes 125. So, this becomes 1 upon 125, 1 minus cosine 5 sine 5 pi x upon L plus blah blah blah. But note one thing, that whereas for displacement these terms were 1 upon 243, 1 upon 325. So, that means that the higher order terms were negligible. Okay. But if you look at this, you see 1 upon 27, 1 upon 125, the higher modes contribute much more, and this is something that higher modes contribute significantly to force. This is again something that we had already said, but here we see this particular case very, very clearly. Now, suppose I were to find out m at L upon 2, which is the midspan moment under a UDL midspan moment. Okay. If I were to find the midspan moment, what would I get? I would get m at L upon 2 midspan moment, right. Midspan moment would be equal to minus 4 P naught L squared upon pi cubed E I, and look at sine pi x upon L. This will become pi upon 2. Okay. So, this would become equal to 1 minus cosine omega 1 t, okay, and then sine pi x upon L, x is equal to L upon 2, this becomes pi upon 2, pi upon 2 is 1. So, it is 1 upon cosine. Then this one sine 3 pi by 2. What is 3 pi by 2? 3 pi by 2 is again minus 1. So, this becomes minus. So, this becomes minus 1 minus cosine omega 3, and this of course is 27 plus 1 minus cosine omega t upon 125 minus. In this fashion it continues, that it becomes plus minus. Okay, this way it continues. So, this is the midspan moment, and this is fairly easy to evaluate. Okay. That is the point that I am trying to make, and this is a fairly easy equation to develop. Okay. In fact, we can easily do it. So, this is how you would solve a dynamic problem. This is of course for a step loading, suddenly applied load, okay, for a flexural vibrations. Okay. Now, let us look at a situation which is a fairly common problem. Let us look at a pile with a suddenly applied load, and this suddenly applied load is of also the same form. P naught. Okay, it's a suddenly applied load, and this load is applied at the tip. Okay, so that is my loading. So I want to find out, and this is for axial vibration. I want to find out axial vibration of pile due to suddenly applied loading. Okay? So, we are looking at an axial vibration. So, what does the equation look like? Well, the equation looks of the type EA this is U okay. As a first step, boundary conditions we know. Okay, we've already done this. Let's look at the second step. The second step is something that we know, which is the free vibration mode shapes and frequencies. I know the mode shapes and frequencies. In this particular case, we've already derived it. The phi n of x is equal to sine 2n minus 1 upon 2 pi x upon L, and omega n is equal to 2n minus 1 by 2 pi EA upon m bar L squared, and this is for n equal to 1 to infinity. Okay. So, now the thing is to find out the generalized mass. Okay. Mn is equal to 0 to L, m bar outside, sine squared 2n minus 2 pi x upon L, the same thing that we did last time, and we get that it is equal to m bar L upon 2, exactly the same way we have done it last time. Okay? And Pn, note that since this is a point load, it's what is going to be over here when we apply this, and so therefore, Pn is equal to P of t into phi n at L. Okay. So, if you look at that, what happens is this becomes P naught when n is even. For example, put n equal to 1. Okay. If we put n equal to 1, okay, we get put n equal to 1, what do we get? We get this is 2n, so this becomes pi x upon L, and pi if you put it sine p upon 2, you get this to be equal to 1. You get it equal to 1. Okay. So, therefore, this becomes this is odd, and this is equal to minus P naught when n is equal to even. Put it equal to 2. When you put it equal to 2, you get 3 by 2. 3 by 2 sine of 3 pi by 2 is minus 1. So, that's how it happens. Okay. So, this is where we get odd and even, we get this. Okay. So, now let us go forward by one step, and that is the third step. We found out our generalized mass and loading. What is the next step? The next step, which is step 4, is to solve the modal coordinate equation. So, Mn plus omega n squared m n y n double dot plus y n is equal to P n, and note that we already know what y n of t is going to be. It's going to be equal to plus minus 2 P naught. Sorry, this is not no longer P naught bar, this is actually P naught. P naught upon m bar L, that's m bar L by 2 omega n squared 1 minus cosine omega n t. So, let us look at the next step, step number 5. Let us look at displacement response. Displacement response turns out to be equal to the following. Now, note that if you look at omega n, what do you get? You get let us just put in this. Let us first calculate this. This becomes this becomes 2 P naught upon m bar L, and omega n squared is equal to 2 n minus 1 into pi. So, this whole squared into E A into m bar L squared. So, m bar cancels, L upon, so this becomes equal to 2 P naught L, 2 P naught L upon E A, right, 2 P naught L upon E A into, now let us see, this becomes 4. So, this becomes 8, and so this becomes pi squared, and I am going to take 2 upon n inside, 2 n minus 1 inside, 2 n minus 1 the whole squared, I am going to take that inside. So, if I take it inside, of course, this one then becomes what? 2 n minus 1 the whole square. That's what I get. That 4 goes up. So, this becomes the, so my displacement response becomes the following. It becomes equal to u x of t is equal to 8 P naught L upon pi squared E A into, now let us see, I have a situation where in the first one it becomes 1 minus cosine omega 1 L t into sine, this is a downward force. So, this becomes, since the downward force, it is minus into sine pi x upon 2 L. Then we have a plus 1 minus cosine omega 3 upon, now this becomes 9, right, into sine 3 pi x upon 2 L minus 1 upon cosine omega 5 upon 25 into sine 5 pi x upon L, so on and so forth. So, these are my terms. So, I can rewrite this in the following format. So, now So, this is ux of t, and now suppose I want to find out my axial force. Axial force response, if you look at P x of t, is equal to E A del squared u by del x squared. So, all that happens is that E A, this E A cancels, del squared u, all that happens is this becomes cosine, okay, cosine pi over 2, and therefore, the following thing happens. This becomes equal to 4 p 0 upon pi. This 1 pi comes out, since the pi upon 2 comes out, this becomes 4. Okay. The L also comes out at the bottom, it becomes pi upon 2L. In every case, pi upon 2L comes out. So, it becomes what? Pi upon 2L. L cancels, this cancels, so this becomes 4 p naught. E A is already gone, and the pi cancels, so it becomes 4 p naught upon pi into, now the minus disappears, okay, it becomes equal to minus 1 minus cosine omega t cosine pi x upon L, again plus 1 minus, I get now here, if you look at it, this becomes 3. So, this becomes 1 upon 3. Okay. So, it is 1 minus cosine omega 3 upon 3 cosine 3 pi x upon 2L, okay, and then minus 1 minus cosine omega 5 upon 5 sine, cosine 5 pi x upon L plus plus plus. Now, note that suppose I want to find out the axial force at 0. What do I get? Well, this cosine pi x upon L becomes 1. This becomes 3 pi becomes minus 1. So, the entire thing becomes this, and so what you get is P at 0 t is equal to 4 p pi. The whole thing becomes just minus. So, this becomes minus outside, and what we have inside is 1 minus cosine omega 1 t plus 1 minus cosine 3 omega t plus 1 minus cosine omega 5 t plus plus plus. So, this in other words is why is it minus? Because it is compressive force. Note that if you have this is this way, is a compressive force, and the minus signifies that it is a compressive axial force. Note something very interesting, and that is that this load is applied, it actually expands over here. What is the reason behind it? Well, let us try to make a plot of this particular thing. Okay. If I make a plot, okay, of the displacement, and I define a parameter, okay, called C, okay, where C is actually equal to E A upon C is equal to square root E A upon m bar, okay, which is actually equal to E upon rho. Okay. This C is known as the longitudinal wave velocity. This problem actually, if you plot this is the displacement wave and this is the stress wave or the force wave, whatever you want to call it. So, if you look at this, if you plot these, you will see that this actually behaves in this fashion. As long as you have 0 less than CT1 is less than L. In other words, this wave that started here at time t equal to 0, okay, how far does it travel? If it takes, see if the longitudinal wave velocity is this, so if you look at T1, it's L upon C. In other words, it's not come up to here. If you plot the displacement, you will get it something like this, where this is equal to CT1. This is how the displacement wave looks. If you plot it between L and CT2 between 2L, in other words, it's come here and not gone back, this thing will look something like this, where this is CT2 minus L. Okay. Similarly, you will get a similar kind of thing where this is CT3 minus 2L, when 2L less than CT3 less than 3L. And now, when you go to 4L, you see this becomes something like this, where this is CT4 minus 3L. Okay. So, in other words, this if you look at actual thing, when you suddenly apply the load, this wave travels from here and comes here and gets reflected. So, when it gets reflected, what you have is you have a combination of a wave traveling this way and you have a wave traveling this way. So, what happens is over here you get a combination of just this wave having come over here. So, this particular value would have come over here, and as it is being reflected, okay, it adds up, and then when it reaches the free end, it actually goes out. And so, once it goes out, that wave is gone, and so now you have a wave which is coming back again. So, this is it repeats itself, okay, every 2L. Every 2L it repeats itself. 2L for time, 2L upon C is the periodicity of this wave. Okay, it's very interesting, and this you can get from this solution. Okay, if you look at the stress, the stress wave, what I call it as the axial force wave. Okay, the axial force wave looks like this. The axial force is a constant, right? Axial force is a constant, okay, and this is CT1, and the entire thing is P naught. So, the wave that comes is P naught. Then you have a situation where you have P naught and P naught. So, you have 2 P naught, where this is C2T minus L. Okay. As you go further, you get P naught and P naught, where this is CT3 minus L. And finally, when you have the last wave, this is P naught, where this is CT4 minus 3L. So, you have the load applied here of P naught, suddenly applied. that sets up a axial force wave which comes here, and as it comes and hits here, it gets reflected, and the stress, since it's a rigid boundary, what happens is the stress wave comes over here and is reflected back. So when you see this is the reflection that goes here. Then it comes, the reflected wave comes here, and then what happens is, okay, because of the boundary conditions are free, part of the wave disappears, and what you have is, now you have a wave coming back, which is only P naught coming back. Okay. Then it comes over here, okay, and these two waves destructive, and when it becomes destructive, P naught and minus P naught it becomes. So this wave goes back, so this becomes the unstressed part, and this goes here. So it goes back here, and after 4L, at 4L you have an unstressed kind of situation. So suddenly applied, it's unstressed, then the wave starts traveling, constructive, so it starts going back as 2P naught, then again because of the free end, destructive, so the 2P naught is coming back, 2P naught is getting reflected, but it's getting slowly added. Then it comes over here, this one gets, now the 2P naught goes back, so it goes back here, 2P naught, and what happens is you get a compression wave. So what you have is, this is a compression wave, this is a tension wave, this is a compression wave. So this is how the entire process of wave happens. So this, what we got over here from those, I'm actually getting you for at any time instant of time x and of t, of course for various components, and c is square root of E upon rho is a longitudinal wave. So this is a longitudinal wave. It's actually traveling along the axis and then going back along the axis, coming back, going back. This is a wave propagation problem. I'm not going to be talking about wave propagation in this course. It will be taken up in a later course, but the essence that happens is that this beauty that you see, it comes from the series solution. Okay, so that's all I have to say. Thank you very much. I've really enjoyed myself in this course, and I hope that you will enjoy this course too. Thank you very much. Bye-bye.